I'd like to welcome Gioele Zardini to the MERL Seminar Series. So Gioele is an incoming faculty at MIT. He recently, I think it was last week, defended his PhD thesis at the ETH Zürich under the guidance of Professor Emilio Frazzoli. And he will join MIT in the fall, and before then make a short postdoc stint at Stanford University in Marco Pavone's group. So we're very delighted to have him here. Today he will talk about co-design of complex systems from autonomy to future mobility systems. So Gioele, please take it away.
Thank you very much, Carl, and thank you everyone for being here. I was telling the organizers that although I'm virtual for now, I look forward to visiting you guys next year in person. So yes, today I'm going to talk about co-design of complex systems, and I'm going to show you some applications all the way from single vehicles, in the case of autonomy, to future mobility systems. And I really want to start from my motivation for this research, which is that I see autonomous systems as a proxy for complex systems. So ideally, what I present today could be scaled to other kind of complex systems. And the second bit is that these systems can promise to have positive societal impact. And now here are some examples. I'm sure you guys are working on very exciting stuff as well. Here there are some of the many positive societal impact that they could have. Autonomous vehicles promise to have safer and efficient mobility. Autonomous robots instead could be used also to explore space. You could use them to monitor environments or to perform search and rescue tasks. And the bottom line here is that the societal impact of these technologies really depends on the technology themselves, but also on the joint design with existing systems. I think a nice example of this is thinking about mobility systems. Here, you typically have to design the single technology, but also you have to make sure that it is embedded in a nice way into the actual existing mobility system. So here in my head, you always have the heaven and hell of the things you're doing. So on one end, for autonomy and self-driving vehicles, you could say that there are studies showing that 30% of the cars would be enough to serve demand, that first and last mile mobility could make public transit more convenient, and also that in the end, everything will be more affordable and sustainable. But also there are studies that show that if you implement technologies in a bad way, you could increase congestion, or the power consumption of these vehicles would make them very environmentally unfriendly. Now, the bottom line for my research is that when designing these technologies and trying to put them into larger systems, we understand well single components, but we still lack a formal and practical theory for performing task-driven co-design of the entire complex systems. And so today's agenda is that I will first motivate a bit more this line of research, and then I will essentially introduce two lines of research. One is the theory of co-design I'm working on, and another one is an extension to deal with strategic interactions. And finally, I will also give you some pointers on future research and what I will be doing at MIT when I join. Now, all of what I'm talking about will be, you can find it on my webpage, and I will provide some pointers for papers at the end of the talk. All right, let's get started. So first of all, what do I mean when I say co-design? I guess some of you joined this talk with some ideas about what I mean with this. And I know this term is a clearly overloaded one, so I want to be a bit more precise. I really think about co-design in terms of minimizing some resource usage and designing something subject to functionality constraints. Okay, so this is as broad as you can get. And I think about the next part of the talk as creating a so-called automated designer, which is something that takes into account some task specification, some multi-domain knowledge, and some design options. And some magic happens, and it produces an optimal design. Now, what does it mean in practice? Think about designing a self-driving vehicle. You can take into account a task, particularly, for instance, a particular environment or a particular maneuver you have to perform. You take into account some robot autonomy and physics principles, and then the actual things you want to design, for instance, components or algorithms, then some magic happens and you can produce optimal designs, for instance, in terms of the energy consumption or the errors with respect to your task. Now, another way to see this could be to design an entire mobility system. Here, the task is the particular demand you want to serve. The principles you're leveraging, or the knowledge you're leveraging, are networks, operations theory, and infrastructure. And then the things you're actually designing are the actual mobility services or the policies you have to put in place. And here, the optimal solutions might be expressed in terms of the performance and the investment you have to put in the system. Now, why is it complicated to make this magic happen for generic systems? Well, there are at least 3 reasons. The first one is that when you design these systems, you have a lot of different components. So imagine designing a fleet of autonomous vehicles. Here you need to take into account actuation, sensing, control, perception, communication, and things are at the software level, but also at the hardware level. And you typically need different people with different experiences dealing with each one of the single components. So the clear reaction is to say there are too many components and so many choices to make, and we have nobody who is able to understand the full thing, the full system. And so this results in a big confusion, and we are typically afraid to make choices because we don't know what the effect of those choices will be. And this is actually the opposite of what we would like. We actually would like to be able to be fast and execute fast assessments of our designs. And in particular, the diagnosis in this metaphor of being at the therapy session is that we need something which is formal, quantitative, but also intellectually tractable. The second complexity comes from the fact that not only we have many components, but these components belong to different abstraction levels. So I could think about the system level, which I design a single component. Then I could think about the platform level in which multiple components have to interact, right? I have a computer, I have a control algorithm, I have a sensor, and here you want to choose the components optimally. Then you have the service level in which different platforms have to be put together and be orchestrated. So here you have problems, for instance, relating to optimal deployment for your fleets. And then the final level is the infrastructure level in which you actually put your fleets into a bigger system where they have to interact with the existing infrastructure, the existing public transit, for instance. And so you see that you have different scales. And the final layer of complexity, if I want to summarize it, comes from the fact that actually you are not the sole designer of your system. In fact, if you think about designing a mobility system in Boston, you actually need to take into account mobility providers, liability companies, policymakers, industry, and also academia and tech developers. And here the difficulty is not only that all of these stakeholders really think differently about the very same problem, but also that they care about different things, right? So the objectives are multiple and sometimes are conflicting. So if I want to summarize these complexities, essentially on one end, we have large systems made of many components and scales, and the nature of these components is heterogeneous, and we have multiple objectives. And the second layer of complexity comes from the fact that we have many agents with different kinds of interactions, and which are sometimes collaborative and sometimes conflicting. Now, in this context, if we want to design a tool which deals with all of these issues, we essentially need these desiderata. So this is something I will come back during the talk, and I will come back to these and we'll try to put some check marks to see whether we were able to address the different desiderata. Here, the first thing is that we need something which is formal and domain independent, right? We need to be able to consider all of these components, the particular knowledge of the field, but we need to do it in a formal way. So we don't need to specify too much our theory. It also has to be something computationally tractable in the sense that we want to be able to compute solutions efficiently. It has to be compositional and hierarchical, both taking into account the nature of the many components, but also taking into account the fact that you have hierarchies of different models. And it also has to be collaborative. So we need to be able to pool knowledge from experts between different fields, ideally, for instance, in the audience of this talk. They also have to be intellectually tractable, meaning that we want to avoid this principle for which the only person that understands the design is a system architect, and the others cannot really help or contribute. And finally, the design exercise should be continuous. So we should be reactive to changes in goals and context. So in this first part of the talk, I will cover the first layer of complexities, which is the fact that we have many components, different natures, and multiple objectives. And finally, I will touch base briefly on the second layer of complexity. So what I'm about to present is a new approach to perform engineering co-design in multiple disciplines. In the co-design here stands for collaborative, computational, compositional, and continuous. And I'm sure we have some creativity and come up with more co-words, but for now, those are the ones I care about. And this is designed to work across fields and across scales. Technically speaking, these tools will leverage domain theory, applied category theory, and optimization. And the roadmap for the next few slides is that I will first present the notion of design problems. I will explain how to model constraints when you're trying to model complex systems in this framework. And finally, I will show you how to solve these problems. So very, very practically, by the end of this first part of the talk, you will understand how to go from the left, which is the co-design diagram, here, for instance, for an autonomous drone, to the right, in which we actually find optimal solutions, here in terms of the error with respect to a task and some power consumption. Now, some of you might be a bit skeptical because you might not have heard of domain theory and applied category theory before. I was in the same exact situation a few years ago, and no worries, this talk is user-friendly, so you will not need those notions. But in the case you know about those, I will highlight some ideas and some context in what I call a pro box, and you will be able to see this. And all of what I'm talking about is part of a large effort, which is summarized in a book I'm writing with some colleagues. And here's the link, and I would be happy to hear some feedback on this. All right, but let's get started. So this framework for performing co-design builds on the concept that when we think about design, we essentially consider three spaces. The first one is the implementation space, or the options we can choose from. The second one is the functionality space. Typically, those options exist because they provide or they make you achieve something. And typically, providing these functionalities comes at a cost or requirements. Now, depending on the field you're from, you might know these spaces with different names. You know, functionalities could be desired behaviors, specifications, objectives, guarantees, and costs instead could be budgets, requirements, dependencies, and assumptions. The key idea is that we will model these functionalities and resources using partially ordered sets. And partially ordered sets are a great mathematical structure that allow to model trade-offs across different fields. So it still allows to model standard costs in engineering, which are totally ordered, for instance, real numbers or natural numbers, but still it allows you to model things that are not comparable. For instance, I could say that I can create a partial order of food preferences in Boston. I could say that I prefer lobster over lobster roll and a clam chowder, but I don't prefer lobster roll over clam chowder, right? I have these uncomparable elements. On a more technical note, I could create a partial order of rules of the road or metrics to evaluate trajectories on the road. And I can use this partial order to actually compare different trajectories and create a preference over those trajectories. Or if you work in information theory or uncertainty assessment for controls, for instance, you came across this other partial order, which is the one of positive definite matrices. Here, the idea is that you can represent each of these matrices as a ellipsoid, and then you can consider the partial order coming from the inclusion of those ellipsoids. So those are just some examples. I actually want to show you that you can do kind of exotic things with these partial orders. For instance, here we wanted to order sensor and algorithm pairs in the context of obstacle detection for autonomous driving. And here, essentially, the idea is that you can characterize the performance of sensors and algorithms by considering these performance curves, such as false positive, false negative, and accuracy rates, Those are quantities that depend on the distance with respect to the obstacle, and you can order these curves by dominance. And now you can create partial orders for each one of these performance metrics, and then you can take the product of those and create another partial order. So all of this is not to go in the details of these examples, but it's kind of to convince you that partial orders are very flexible and allow you to model different things. And for the next slides on, I will assume that functionalities and resources are partial orders. Now, how do we use those? How do we use functionalities and resources? Well, it's true that from the practical point of view, we care about implementations and the functionalities and resources they provide. But really, what we care about is feasibility. So this is probably the only formula you will see in this talk. As I said, I want to keep it user-friendly. The basic idea is that we want to assess feasibility given a certain functionality and given a certain resource. So let's say I give a certain functionality, a desired behavior, and I give a certain resource or a certain budget I have available. And now you want to answer the question, does there exist an implementation in the implementation space such that I get at least the functionality I desire, at least the desired behavior I really want to reach, by requiring at most the budget I have available, right? And here you could think of it as a particular task for a robot, for the functionality, and the budget being, for instance, a monetary budget or an energetic budget. Now, this is technically called the Boolean profactor. And it's a monotone map in the sense that if I lower the functionalities or if I become less picky, I will not require more resources to achieve them. And on the other hand, if I suddenly have richer, if I allow more resources, they will not provide less functionalities. And in the next few slides, I will represent functionalities as continuous green wires on the left, and resources are dashed red wires on the right. So now, this is the central notion for co-design. We have a feasibility relation, or in other words, a design problem. And now what we want to know is how to use these design problems. So in practice, how do we populate these relations? So the first way is to use catalogs, right? But the same existence of a particular component is a proof that there is some relationship between certain quantities, right? You can think about a battery, but also you could think about having a spreadsheet of the latest drones, drone technologies, and they have certain properties, and each particular technology is a relationship between some of those properties. Sometimes you don't have catalogs. Sometimes you can just use first principles or analytical relationships. For instance, in the context of designing a drone, I know that the energy required by a mission will always be greater or equal than the duration of the mission times the actual power consumption for the drone. And in most of the cases, you might say we neither have catalogs nor first principles. How do we deal with that? Well, actually, you can populate these relationships also with a data-driven or on-demand approach, right? Sometimes you just have a sequence of data points that characterize feasibility, and this can be constructed incrementally. And ways to obtain those points could be experiments, simulations, or actually solving other optimization problems, right? So this is kind of showing you that that populating this feasibility relationship is flexible, and you can actually choose the kind of methods you prefer. Now, let's so far everything is in theory world. I want to show you some practical instances. I could think, for instance, about designing an electric motor, and this is a specific relationship between the achievable speed and the torque it provides to the cost, mass, and current it requires. Or I could think about designing an autonomous vehicle as a relationship between the speed, the achievable speed of the vehicle, while maintaining certain guarantees of safety, and a task, a particular task you want to perform, and fixed and operational costs. Or I could think about the service level. I could think about an area to cover, and I have a swarm of drones, and I want to minimize the speed of each agent, the number of agents, or the time needed to cover the area, or the total cost involved in the operations. Finally, I could also think about designing an infrastructure for a mobility system. Here, I think about the demand as the functionality provided, so I will satisfy a certain demand, and the requirements to be minimized are the investments or the externalities. Now, we can reason about the wires. whether we need more, whether we need other wires. Here, I just want to convince you that this really is something that scales across disciplines and across scales, and it's really applicable to many different domains. So why do I like this approach? Why are we coming up with this kind of exotic way of thinking about design? Well, you can take the notion of a single design problem, of a single block, and now interconnect this with other design problems. And you have a rich algebra of ways in which you can do that, right? You can put them in series, you can have them in parallel, you can have feedback, you can have a choice between two options, or you might be willing to be robust between two options. And combining these design problems in these different ways still returns a design problem. So still returns a mathematical object that has the same properties. So this becomes a very handy tool to decompose large problems that are made of many components into sub-problems and their interconnections. And you can do this on a graphical level, and everything mathematically will work out in the background because there is a category that we can define where all of these compositions are well defined, and this category namely has some particular properties, okay? But so the reason why we really like this is that the notion of composition is well defined. Okay, then going back to the original quest, this is something which is formal, right? I kind of convinced you, I guess, that this is applicable to different domains, and this is compositional and hierarchical by nature. So compositional in the sense that they can interconnect multiple components, but also I can suddenly draw a box around some interconnections and put this box into a larger diagram where I have multiple interconnected components. Now, all of this is just talking about problems. Here, I want to spend a minute talking about solving these problems, right? What does it mean to solve a design problem the way I presented it so far? Well, we have essentially two queries. The first one is, given some functionality I want to provide, given some desired behavior, what are the minimal resources I require to provide it? Or what are the implementations or the particular solutions that allow me to minimize the resources? And then I have a dual one, which is, given a certain budget I have available, what is the maximal functionality I can get out of that, right? Now, the two problems are dual technically, and we will focus on the first one for the sake of the narrative. And a bit more precisely, what we are looking for is a map from functionalities to upper sets of feasible resources. Or, if I care about the optimal solutions, a map from functionalities to anti-chains of minimal resources. Now, anti-chains is a technical term, but you might have heard of Pareto fronts. And those, in this example of a drone designs, where we compare power consumptions and tracking error, those would be the points here. So those are uncomparable minimal solutions. And the upper sets instead would be the red area that dominates those points. And so we actually want to find this map. And let's try to frame this as an optimization problem, right? Since this is our background. This idea gives rise to a family of optimization problems, which are given by a graph in which a node is a design problem and the edges are the different interconnections. The variables of this optimization problem are the functionalities and resources and their respective partial orders. And the constraints are of two kinds. The first one is that each node should be a feasibility relation, a design problem. And the second one is that whenever we have an interconnection like the one shown here, where we have a co-design constraint, essentially we are saying that the resources required by a component should never exceed the functionality provided by another one. And this is a very intuitive meaning, right? If I have a process that requires some energy, this energy should never exceed the one that is actually provided by another process providing energy, right? So whenever you see such a constraint, we really mean this. And the objective of this problem is to minimize resources, right? So I fix a functionality and I want to minimize resources. Now I want to briefly notice that so far I just assumed functionalities and resources and feasibility relations, and I never said that this problem is convex, differentiable, continuous, and actually not even defined on continuous spaces. You could have a mix of continuous and discrete spaces, okay? So the first reaction to this is, well, you're presenting something which is a bit exotic. It does not even have the properties we will look for. So what are you talking about? Can you even solve this? And the answer is yes. So again, the technical tools we are using to formulate this can come into help. And the idea is that we can find a compositional solution approach. So we are teaching a class on this subject, and there is an entire 2 hours class dedicated to showing how. Here, I want to give you the take-home messages, and then maybe in the spill out, we discuss about the details. The main idea is that in these graphs, it's very easy to get these map from functionality to anti-chain of resources for the single blocks of these diagrams, for the single design problems, right? This is very easy. Now, what is difficult is to find the map for an entire graph, given the knowledge of the single maps. And here, the compositional approach comes into play because it turns out we can write the solution of the single compositions of these maps as the composition of the single solutions. Or in other words, it's enough to design some composition functions for the different compositions we have that combine these maps. And in technical terms, this means that you can find a formula that amounts to a least fixed point of a particular monotone function. And evaluating this formula essentially gives you the solution, okay? The reason why all of this works is because there is a functor between two particular categories, one of problems and one of solutions, but there are two good take-home messages. The first one is that first we can design an algorithm and have a complete solution. So we are guaranteed to find a set of all optimal solutions or a certificate of infeasibility in case we don't have solutions. And the second one, which is the most important one, is that the complexity of solving these design problems is not combinatorial in the number of options for each component, but rather linear, right? So if I have different design problems that are interconnected, and I have A options for one component, B options for another one, and C options for a third one, actually the complexity grows linearly in these options and not combinatorial, which is a strong result. Then you might ask, okay, but where does the complexity come from? It comes from these code design constraints, and I will briefly mention this in a few slides. So the take-home message here is we have a nice way, an intuitive way to represent design problems. And this leads to a class of optimization problems that can be solved efficiently. So it is computationally tractable. Now, this so far seems a bit abstract, right? And so you might wonder, where's the catch? And all of I presented so far is the developer viewpoint. So all of these feasibility relations, the interconnections, the functors, the categories. But actually what matters for the user is being able to specify those components. And given once you have specified the components in a particular diagram, actually solve optimization problems. And for these problems, there is a dedicated language, which makes it very easy to specify problems. And there is a dedicated solver. And now, in few months from now, there's going to be also an online interface for you to play around with these things. And we're actually organizing tutorials at major conferences to help people play around with these tools. So this is just to convince you that you need very few, maybe a couple of hours to get up to speed with this framework and start using it for your problems. All right, so now that I talked about the theory, I want to show you some practical things, how to actually use this to solve problems. And in particular, I want to guide you through a modeling approach and coming up with the actual implementation of this. So the main idea behind this, using this framework, is that you should define the task for the system you want to design. So for the narrative of this talk, imagine that we want to perform urban driving. Right? This is the first step you need to achieve, is defining the task. Then you need to decompose the task from the functional perspective. So urban driving is a mixture of many functionalities, one of which is following a trajectory. And following a trajectory is a mix of performing lateral and longitudinal control. Now, longitudinal control itself is a mixture of speed tracking and emergency braking. And you can go on and on until you reach the level of granularity you like and you care about. Then the second thing is, once you decompose these tasks, you want to find the components, right? And when you look at the diagrams you see in this talk or in my papers, you look at diagrams that are of the second sort and not of the first one. So we're used to look at those diagrams in the controls or data and information flow perspective, where you have a sensor that produces some data, for an estimator that produces an estimate, for a controller that produces a command. Instead, here, we really care about decision-making that requires a state estimate, that in turn requires some data, an algorithm, some computation, that requires sensors, programmers, and computers, and so on, right? We care about logical dependencies. So you should look at these functional decomposition and highlight components by performing this functional decomposition, by this logical decomposition. And once you have done so, essentially you have found many blocks for the subtasks that you can interconnect based on the interactions of these tasks. And you have to highlight what are the common resources, right? So for instance, in autonomy, the common resources are typically the size of the robot, the cost, the weight, the power consumption, and the computation requirements. Now, the question that might pop up is, what is feedback? I mentioned before that feedback is where the complexity happens. And here, really, there are two interpretations. One is the physical one. For instance, a robot might require actuators to move. The actuators must be powered by a battery, and this battery must be carried by the drone. So the more actuation I require, the heavier the drone because of the battery, but then the heavier the drone, the more actuation I need. So this is kind of the feedback in the physical sense. In the abstract sense, you could think of it also in engineering versus business case perspectives. So for instance, a component must support certain behavior. The behavior must be implemented in a way that justifies the cost, but the budget must be sufficient for the components to actually exist. And there are a number of, in the case studies I will show in a minute, there are a number of those feedbacks. For the robotic part, the classic ones are computation, power, or weight, for instance, of the robot. Here, for instance, if you think about a mobility system, you might care about the fact that the investment you put into your system are somehow compensated by the money you can make out of the mobility service. So now you are at a level in which you perform this decomposition, and so you are ready to essentially write a skeleton. So you want to write these co-design diagrams, and you want to do it even before thinking about how to populate your models, how to populate these feasibility relations. And now you might wonder, okay, but how do I choose the wires? Here, the context informs the level of detail, right? I can think about designing an autonomous vehicle as a back of the envelope calculation, where I think about this as a relationship between speed and some costs, but I can also do this from the autonomy design perspective, where I maybe want to specify the particular tasks, the environment, the power consumption, the emissions, or some danger and discomfort models. And the second thing is that once you have this skeleton, you start populating your models with the different tools I presented. And now there are certain things to point out. First of all, sometimes you are unsure about certain components. And with this framework, it's very easy to embed assumptions, right? You might not know how a component behaves, but you can, for instance, assume worst case scenarios, best case scenarios, or everything in between. Sometimes technologies don't need to exist already. They can be parametric with time, right? Here, for instance, we are working now with a company doing racing, designing racing cars, and they're saying, okay, what if we design these components and make sure that this component has these properties? Would it change the optimal solutions at the system level? Yes or no? And this component is not yet even in the plans. They don't even know how to do it, but they're just testing whether something would work in the future. And the final thing is, although all of this was done in our lab, actually this can be decentralized, right? Different people can work on the different components in a decentralized fashion. So going back to the original quest, we have something which is continuous, collaborative, and also intellectually tractable. So now I want to show you this framework at work. So let's say we start with the decomposition I showed before. We can come up with a co-design diagram like this one, where you have essentially the longitudinal control, lateral control, but also the design of the vehicle itself, the design of the sensors, both the placement of the sensors, but also the actual algorithms you use for perception, and the actual implementation of the controllers. as well as the computers and models with which you evaluate efforts, errors, and discomfort. Now here, you can populate these different models using different techniques. One for controls is typically simulations or optimization, solving optimization problems. You can populate computers and vehicles simply by taking off-the-shelf components. And for sensors and algorithms, you typically have benchmarks, or you can take performances out of existing data sets, for instance. Now, the idea is that when you have such a diagram and you also populated the different feasibility relations, you can now start solving some optimization problems. So you can fix a particular environment, you can fix a task. Here, for instance, expressed in terms of the maneuver the vehicle has to perform and the speed at which it has to perform it. And fixing this task, you query the solver to actually minimize resource consumptions. And here, resources, for instance, could be the control error with respect to the original maneuver you have to perform, and the actual cost of the autonomous vehicle. And here you see that you have different solutions, right? Each point on this curve is a Pareto optimal point. And for the different solutions, you can retrieve the details about this optimization query. So you have a particular controller with particular properties, you have particular sensors, you have particular computer. And you see that different solutions have different implementations. You can very easily switch the actual maneuver or the actual task, and also switch the kind of things you care about. Here, for instance, is our trade-off of control and error and control effort. And you get to see that you can highlight different trends, right? So I really think about these trends. You know, one can always sit down and improve the models, but I think it's important to look at the trends and look at the kind of trade-offs, and this helps the designers think about decisions with respect to components. Another thing to notice here is the monotonicity in the task complexity. You think about the task complexity as increasing the curvature of the maneuver and the speed at which it has to be performed. And essentially by increasing those, by making the task more complex, you also increase the resources you need. And you see that those Pareto fronts dominate each other. All right, so I guess I gave you an idea of how this works. And now I want to take a step back and show you how to take this model and embed it into a larger one. So in the beginning of the talk, I was talking about societal impact and mobility systems, actually, right? And here I want to show you a problem in which, the solution to a problem in which you now take the perspective of municipalities, and you now want to decide how many vehicles you should allow in a city, which kind of vehicles, what kind of performance should they have, and also what kind of investments you want to put in your infrastructure. And here, again, this is a design problem. The task here is the demand. And here, the idea is that you want to design the mobility solutions together with the network they enable. And here, it's not anymore something that has to be solved within a autonomy research group, where different people work on different parts of the autonomy. But here, this really involves different people, you know, transportation people, autonomy, economics, policymaking. So the compositionality of this framework allows you to put this block inside a larger diagram, where now we are modeling an intermodal mobility system, in which you not only have a fleet of autonomous vehicles providing mobility services, but also you have micromobility options and the start-down public transit. Here, you can take this complex model and put it into a box, which is embedded into a larger design one, which mixes the design of the public transit, the autonomous vehicles, the micromobility options, and the intermodal orchestration of all of those modes of transport together. Here, the demand is the task, and the actual resources required are the investments, the externalities, and the average travel time in the city, or the performance of the system. And now, in the very same way, you can fix the demand and minimize the costs, for instance. You can do this, for instance, we took here the case of Washington, D.C. You take standard data sets for demand, you take the data from the networks, and you really populate, for instance, the orchestration using a simulator or using an optimization problem for flows. And what you get is a trade-off between the average travel time and the investments you put in the system, right? So you see that the more investments you put, the more you lower the actual average travel time. And for each one of these solutions, you get not only the number of vehicles in the system and their speed, but also the details about their autonomy stack. And in the same way, you also get the number of electric vehicles and the number of trains for your subway system. So with this framework, you are suddenly able to find solutions all the way from single hardware, software components in a vehicle, all the way to the actual society scale system, right? And I believe that the kind of trade-offs we are showing are really important for people making decisions to reason about the complexity of these issues. All right, so now I want to briefly go over the next challenge, which is, I will briefly introduce it, but it's mainly one of the challenges I will have when I will join MIT, which is dealing with strategic interactions, right? So now when looking at this final design diagram I was showing, it is pretty clear that you cannot take the perspective of a municipality, assuming that the municipality makes all the decisions, right? So here we can, unless you have dictatorships, here really what you care about is modeling different stakeholders that make design decisions within the same framework or the same environment. So rather than thinking about optimal designs, for this kind of applications, we should be thinking about equilibria of designs. And therefore, we should go towards a theory of co-design games or co-design interactions, which is something I want to get to at some point. And here we have two basic milestones towards these games. One is identifying that partial orders and monotone relationships between them play an important role when defining these design problems. And so what happens if we extend these notions to games? So we created the notion of posital games, and I will talk about this. And the other one is that realizing that those interactions typically happen in a hierarchical way, and you can actually create the mobility games, and you can solve these games using particular tools from game theory. Now, the second part, for the sake of this short presentation, will be left out. I'm happy to discuss it offline. And I will now try to show you the first part in the remaining minutes. So here is really about behavior specification with multiple agents. This is kind of the background. And the observation is that when we are designing these systems, we are getting closer to natural sciences as engineers, because we are creating things that we do not fully understand, and then we study our creations. And in this part of the talk, I will essentially talk about the fact that we have two challenges for decision-making in this context. We, first of all, have existing rules that are written by humans for humans. And second, that the systems we design need to be robust to unconstrained environments in which there are interactions. So if you think about behavior specifications for robots, in particular here, autonomous robots, autonomous vehicles, here you need to take into account a number of things that is across different domains, right? You have culture, the actual function of your vehicle, ethics, safety, liability, compliance to traffic rules, courtesy or comfort. And you also have something which is really cultural, right? For instance, in Boston, there is the so-called Boston left, and this is pretty hard to embed into your rules. And in this context, it is important to, first of all, certify vehicles and drivers, define the rules of the road, and then enforce them, right? But sometimes those can be a bit tricky to enforce or to interpret, right? For instance, in Switzerland, there is a rule which says that all road users must behave in such a way not to pose an obstacle or danger to other road users, which simply means that if you are about to pose an obstacle or danger to someone else, you could violate some other rule, right? So there is already a notion of hierarchy between those rules. So the typical way to think about behavior specification in this context is to, first of all, think about R constraints, like I don't want to do this, I don't want to do that. But the issue here is dealing with infeasibility. And typically in the literature, when you start to consider other actors, it's hard to find guarantees for the algorithms that coordinate these actors. The other approach could be to do case analysis and or finite state machines, but this is something hard to do because you have to consider all the cases, and there is this statement that says if statements kill people. And another typical approach is just relaxing, right? You take into account everything you care about and you relax it into a scalar cost function. But this is very hard to retune for different scenarios, and it's not transparent when things fail and you want to understand why they failed. So, okay, again, I'm criticizing the status quo. We as a researcher, we should not throw the ball to other stakeholders or incorporate our own beliefs in these algorithms for behavior specification. What we should do, again, is creating something which is intellectually tractable and transparent, customizable, and we should be able to engage with stakeholders. So the thing I'm presenting now builds on some idea on minimum violation planning, which was developed actually at MIT by people including Yana Tumova, Sertac Karaman, and Emilio Frazzoli, my advisor. And here the idea was that you start by assuming that some constraints will be violated, and you want to find alternatives that least violate them, right? So you define rules you have to follow as a total order over certain realizations. And here is an example, for a taxi, safety is important, then compliance to rules is the secondary importance, comfort and performance follow. Then for a race car, instead, compliance is very important. If you know what to be kicked out of the competition, then you have performance, safety, and comfort. Now, this tool has been proved to be very efficient when you want to define behaviors in a modular way. And it's easy to do what the car will do or why the car did something, right? And it turned out to be very practical also because you can introduce tolerances. However, as I showed in the first part of the talk, sometimes rules are not comparable or sometimes objectives are not comparable. How do you deal with that? So there was a tool that leveraged the fact that rules can be uncomparable, to which we refer to as rule books. And this was developed in a company that's now called Motional. And this highlights the fact that you could still have the total orders between rules, but still you could have things that are not comparable, right? So that you don't prefer one over the other, or things that are indifferent, where really it doesn't matter what those rules represent because they are the same to you. And in this toy example that I was already showing before, starting from a partial order over certain metrics, you can come up with orders over the actual trajectories. And now the rule books approach was used in motion planning in the way that you mix creativity and good taste, right? So there is here a citation from Linus Pauling, which says the ways to get good ideas is to get a lot of ideas and then throw away the bad ones. So practically speaking, what happens is that in the planning block of your autonomy stack, what you do is you have a creativity part in which you want to propose new trajectories, and then you want good taste or quality when scoring those trajectories. And the scoring here happens at the level of these partial orders. So what was done in practice was taking the rules of the road for various countries, which actually was about to be 200 rules in 20 different groups. And it was pretty practical for performing motion planning in different countries with different usage and costumes. Now, all of this was just considering ego agents. And now the question we want to answer with the strategic interactions is, how do these specifications work when you have multiple agents? So in particular, when you consider games, you typically have players which choose a scalar utility function. Based on the preferences of these utility functions, they decide an action from their decision space. Given the joint actions of all the players, you then decide a game outcome. And then finally, you find equilibrium. The only thing we changed to go back to the co-design thing I was describing is we switched to the case in which each player has a partially ordered preference over a set of metrics. And in particular, we analyze this in the context of game theoretic motion planning, where you have different vehicles that have to interact, for instance, in an intersection without knowing what the others are going to do. And we want to analyze the equilibria of these setups. Now, in very brief terms, we can discuss more in the spillover. We define a class of game called posital games, where we extended the standard notions of game theory to this setup. And we provided sufficient conditions for the existence of Nash equilibria. In particular, you can prove that for certain scenarios, such as the urban driving one, these gains are potential gains of a particular kind, and therefore you can compute equilibria. The second thing is that you can characterize the efficiency of these equilibria to be able to decide which ones you want. And finally, the most important one is that this idea of having partial orders of rules allows you to gradually refine the preferences of each player, and for instance, via an estimation process. And given these refinements, you're also able to refine equilibria. So this new way to perform behavior specification is very practical when performing estimation of the preferences of your opponents. And so those are some plots for the different scenarios we analyze. This is now open source. We worked on data sets such as the ones provided by Common Roads for motion planning. And this is everything is reproducible, and it's also work in progress for extensions. So now I want to use the maybe couple of minutes, and then I'll free up for questions. Apologies if I'm a bit late. To what I want to do in the future, and actually this is important because I will be very close to you guys, and maybe we find ways to collaborate. I essentially see my future research with three main steps. The first one is modeling and foundations, algorithmic foundations. The second is societal applications, and the third one is user-friendly tools. So in the first one, I showed you a theory of co-design which works, but still this is the first step in a very long process, right? We need to improve the current algorithms for solving the problems, but also allowing more flexibility with modeling these problems. For instance, you might want to say that you don't want to populate your feasibility relations beforehand, but you want to do it online, and then you have to have a notion of sampling those different models, how you do that, and so on. You also want to take things that are already done in certain sub-disciplines and try to embed them into these larger design diagrams. And finally, we want to come up with these co-design gains. In terms of applications, you kind of seen the main ones, autonomy and mobility, but there are many other ones, right? For instance, now we're working on infrastructure problems for autonomy, infrastructure for energy, where you have to place charging stations, but also decide the energy infrastructure to support new technologies. And this is only from the autonomy and mobility sides, but actually we have a number of collaborations with applications in aerospace, automotive, production chains, and even data networks. And finally, as you have seen, if you visited my webpage or if you follow me, this is meant to be a user-friendly tool, but it's still something a bit exotic. So really, towards making it user-friendly, I really want to interact with more industry partners and authorities. And as you see, I'm organizing this literature, writing this book, but also workshop, online classes. I really want these tools to get out and people to start using them and reasoning about them. And since the background needed to understand them, it's not really a common one that's taught in classes at universities. I'm really pushing hard to make sure that this goes out in the public, and I would be happy to discuss with you any ideas you have regarding this. So summing up, I hope if you take away a couple of messages from this talk is that today's systems, autonomous systems, require new tools for their design to be efficient and usable and intellectually tractable. And also that for certain systems, we need to perform strategic interactions, and therefore we need to be able to model them. Now, those are some papers that I can refer to later if you're interested. And I want to thank some collaborators for these works, both students that helped me getting some of the results, but also mentors that I had the pleasure of working with, and some acknowledgement from funding from ETH Zürich and Stanford, and also some small advertising I'm hiring now for my group at MIT. So if you're interested or know anybody interested in joining the group, feel free to reach out. And with this being said, I open now the stage for question, and I am excited to hear what you think about all of this. Thank you.
Thank you so much for the very interesting talk. Any questions, comments? So I have a question to start with. You said that this is computationally tractable. What are the, can you be a little bit more specific on that? What do you mean with tractability here?
Oh, yes. So it's, essentially it is computationally tractable in the sense that there is an algorithm. You can, for these optimization problems, you can write an algorithm that has a linear complexity in the options you are iterating over and non-combinatorial. Whereas in the state of the art, typically you have combinatorial explosion for these design problems, right? So this becomes very important because when you have, imagine you're designing an autonomous vehicle and you have choices of sensors, choices of where you put the sensors, choices of which algorithms you use to perform perceptions with the sensors. And then you have choices of control algorithms and choices of planners and choices of actual computers you put on the actual chips you put on your vehicle. And imagine now the complexity of solving this problem being combinatorial in all these possible combinations. That would be bad, right? Instead, here we have a result that shows that this is linear in these options. This can still be huge, right? But at least it scales linearly.
And how big is this for the examples that you presented here? Ballpark numbers.
So you can imagine that for each one of the blocks I was showing, you have between, for vehicles, we are iterating over hundreds of possible vehicles. For sensors, we are iterating over millions of possible combinations of sensors, placements, and algorithms. And for controls, also hundreds of thousands of possible iterations, different parameters, different control algorithms, different setups. So we are trying to do it realistically, right? It's not a toy example, I would say.
Mm.
Now, an important point here that I think you gave me the assist to talk about this is, the way it works now is that you specify these feasibility relations and then solve the problem. Whereas what you want to do in practice is knowing the process you would use to generate these feasibility relations. For instance, for a control problem, you want to know what's the optimization you're solving. For a benchmark of a sensor and algorithm pair, you have a data set from which you are performing some computation. But what you would like to do is, starting from a task, optimally sample the particular models with the minimum number of implementations, with the minimum number of options you actually need, and not pre-compute all of them and then solve, right? You see what I mean? So you would need an online an adaptive or online framework to do that. This is something we have not done yet, not because it's complicated, just because we're the first people working on this particular framework. But it's the challenge there is that all of this is as a particular structure. It's not, for instance, differentiable, right? If this was just a differentiable simulator kind of framework, we could use that to perform gradients and solve this problem. Whereas here we have partial orders and relationships between partial orders. So we need to find the right abstraction and the right algorithms for this. But this is some of the next challenges we have in front of us, for instance.